everybody's seen the moon. We see the moon so often that we sort of think we know about the moon because, I mean, there it is. You can point to it. It's real easy to find in the sky, unlike a lot of the things that we enjoy looking at. But the moon has phases, as we've all noticed. That is, it changes its shape as seen from here. And it doesn't change its shape as seen from the moon. The moon remains pretty much what it is. But two principles. One, that the moon orbits the earth. Okay, that's something that the ancients knew very well, but they thought everything orbited the earth. What they didn't know, some suspected, that the moon shines by reflected sunlight. Again, to us that seems obvious because we've known that pretty much all our lives. But it's not obvious to someone who doesn't know the discoveries of the past 400 or 500 years. It was thought that not only the moon, but the planets all shine by their own light. And Galileo had a hand in debunking that. The inner circle shows the moon as you would see it if you were above the Earth's North Pole with the lighted surface, the sun over here, and the sun really far over here, like 400 times the Earth-Moon distance. Also, this is not to scale. The Earth-Moon distance is about 30 Earth diameters, so that's not to scale either, but we don't need it to be to scale for this. And the outer circle shows the moon as it appears from the Earth, that is, as it displays its phases. The new moon, where its lighted surface faces the sun, but its dark side faces the Earth. And then through crescent, first quarter, and so on, and we'll discuss those in just a minute. These are the approximate times of moonrise transit. Transit means going across the meridian that you happen to be on, and moon set. Now, circumpolarity, this is something that Bill Buswell discussed in detail in our last session. Circumpolarity means how close a celestial object is to the celestial pole. That is, as seen from the northern hemisphere, Polaris, the North Star, never sets, and neither do several constellations that surround it. However, the farther south you go, the less time anything spends above the horizon, and once you get to the horizon, which here at our latitude of 35 degrees north, the farthest south you can see in celestial latitude, so to speak, or declination is negative 55 degrees south. Is as far south as you can see. So anything 56 degrees south doesn't rise at all here. You can't see it at all, okay? And the further poleward something is, the earlier it's going to rise and the longer it's going to be up. So that when the moon in its orbit around the Earth and the Earth's orbit around the sun, as the moon makes its way against the background stars and constellations, it follows the ecliptic. Well, the ecliptic is on the zodiac. And the constellations that make up the zodiac, some are pretty far north and some are pretty far south, so that when the moon is in one of the southern constellations, like Scorpius, say, or Sagittarius, it's going to rise a little later and it's going to set a little sooner than it would according to this table. But let's go back and review all of this. Okay, new moon, that's here, is going to rise with the sun. Well, why is that? Because it has to, because the sun is over here, they're pretty much aligned, and so we're observing from this point, and we look out here at the new moon, which we can't really see because it's just the dark, and it's so close to the sun in the sky that we couldn't see it anyway. It's going to be dark. You can't really see it. And since it rises at sunrise, it's going to transit about 6 hours later. It's going to be up roughly 12 hours, give or take. So it'll transit around noon, and then it'll set with the sun, but again, because it's so close to the sun in the sky, it's going to set about sunset. The next phase, the waxing crescent, waxing means increasing, is this sort of familiar sight as seen from the Earth. It's going to rise sometime in the morning. That is, it's because the moon is traveling eastward in its orbit, and it's going to travel, it travels eastward at about its own diameter per hour. That is 30 arc minutes, or roughly half a degree per hour, the moon's passage eastward. So that after the new phase in the waxing crescent, it's going to rise sometime in the morning, it's going to transit sometime in the afternoon, it's going to set in the evening. And we've all seen the crescent moon in the west, early evening, just after sunset. That's that phase. Then you get to first quarter. Now, here's getting ahead of myself a little bit, but that's the proper term for this phase of the moon. People will talk of the half moon. Okay, it's a half moon in the sky. Well, there would be a half moon in the sky not only at first quarter, but at last quarter. So if you, say a detective was taking evidence and the witness said there was a half moon in the sky, and the detective writes this down, well, later on, well, geez, which half moon was this? So it has to be specified. This is the first quarter. It's a quarter of the way around in its orbit. And it's going to rise at noon, or roughly noon. It'll transit at sunset, and that's what we see in the early evening, about a week after new moon. You go out, and right on the meridian, you're going to see this bright, half-lit first quarter moon. And then it's going to set sometime in the evening, or set at midnight. Next phase is waxing gibbous. Waxing, again, meaning increasing. And gibbous comes from a Latin word that means humped or hunchback. And the moon, it has this sort of oval shape in the gibbous phase between first quarter and full, also between full and last quarter. And the waxing gibbous is going to rise again because the moon is moving eastward about its own diameter per hour. Well, having risen at noon at first quarter, it's going to rise sometime after noon in waxing gibbous. It'll transit sometime in the evening, and it'll set in the early morning. Okay, you're kind of catching on to the pattern here. Full moon, when it's fully illuminated, is going to rise at sunset. It has to, because it's opposite the sun in the sky. And it will transit at midnight, that is, go right across the meridian, see the full moon right up and down in front of you, and then it will set again with the sun at sunrise. Waning gibbous, okay, between full and last quarter is going to rise sometime in the evening, transit in the early morning, and set sometime later in the morning. Last quarter here will rise about when? If you read ahead, you already know the answer. Okay, it's going to rise about midnight, just about midnight. And then it will transit at sunrise. This is if you are an early riser and you go out sometime around sunrise, very slightly before, and you can look up right where the first quarter moon was 2 weeks earlier. There's the last quarter moon, but instead of early evening, it's going to be very early morning. And then it sets about noon. And then the waning crescent will rise sometime early in the morning, will transit sometime in the morning, and it'll set in the afternoon. Now, we talked a little bit about earthshine, and that's as distinct from moonshine. Moonshine in this part of the country means something entirely different. That's why, maybe why the Beethoven sonata which in German is called the Mondschein, is not translated moonshine in English. It's instead moonlight. But anyway, the sun's light is reflected twice. That is, it hits the earth, it bounces off the earth, hits the moon, and then is reflected back. And this is sort of the way it looks with the English saying is the old moon in the new moon's arms. So like this. You see it best at the time of the crescent moon, when the glare of the rest of it, when you get into a waxing gibbous or waning gibbous, it's hard to see because the rest of the moon is so brightly illuminated that you have a real difficult time seeing the light reflected from the earth. And so this is the best time to see it, and that's the full earth as seen from the moon. Okay, we think that maybe when you see the full moon, you're seeing all there is of the moon. The same face of the moon is always toward the earth, and we'll get into the reason for that shortly. But actually, you can see more than that. To the first approximation, we see it all the time. It rotates once on its axis as it makes one revolution around the earth, both in the same direction. But we can see about 10%, 8 to 10% more of the moon than we can see at the typical full moon because of libration. Now that comes from that's a Latin term, comes from the word for scales, Libra. And if you see a drawing of the constellation Libra, the drawing that accompanies it is it's a balance. When you put a known weight on this side, you put the thing to be weighed on this side, and it goes like this until you get an equal weight. Well, that's the metaphor here, that the moon is wobbling a little bit as seen from the earth because it actually is wobbling. Its rotational speed is constant. That is, on its axis, it turns at the same rate all the time, but its orbital velocity around the earth is not, okay? The closer in to the primary body an orbiting body is, the faster it travels, the farther away, the slower it travels. It's kind of this zoom, zoom, this kind of thing. This is why comets, when they are orbiting the sun, as they approach the sun, that's when they're going the fastest. And then they zoom past the sun, if they're lucky and don't get eaten up by the sun, and they zoom out. And then once they get to the farthest point away, such as Halley's Comet, which approaches the sun about every 76 years, it gets out to its farthest point and it slows down to almost nothing as seen from the earth, if you could see it, but it's too dim to do that. So it's sometimes the rotation of the moon is a little bit ahead of its revolution, so sometimes behind because of the differing speed of the moon in its orbit, and that lets us see around its edge. Also, you can see above and below the poles of the moon because its axis of rotation is not perpendicular to its orbit. It's inclined about 6.5 degrees. As you remember from last time or grade school, the Earth's axis is tilted about 23.5 degrees to its orbital plane, and that's the reason we have seasons. And so this lets us see over and under the poles of the moon. And during each night, because the moon is traveling about its own diameter per hour, and the Earth is moving somewhat slower than that, it's moving, faster than that beneath the moon, you can sometimes see around the edge of the moon to a small extent. Now, we've already touched on one of these, the misnomers, the half moon. Okay, we've already talked about that. First quarter or last quarter, because you have to be specific about it. It could be a half moon, could be either. Dark side of the moon, okay? The moon does not have a permanent dark side. It always is lit to some degree, with the possible exception of some craters at the poles that remain in darkness. But the moon gets lit all the way around what we mean by that, what most people mean, is the far side of the moon, the side that can never be seen from the Earth. They're talking about the dark side of the moon. Well, there's always a dark side of the moon, but sometimes that's the side we can see, except when it's really dark. In cartoons, you'll see this kind of representation of the moon, and you have to put this in context. It's 2 in the morning. Well, you're not going to see a crescent moon like that at 2 o'clock in the morning. It's just not going to happen. This one is a little more accurate in a way that, okay, this is a crescent, and here's Dagwood Bumstead upbraiding his son for coming in late, as if this is a moon as it looks when it's very late at night. Well, in the northern hemisphere, no, that's early evening. That's the waxing crescent. Now, if the Bumsteads lived in Australia, that would be accurate, because that really is how it looks. And then this one, the moon does not ever look like that, not ever, except in a partial eclipse. So just, trying to get this over to cartoonists is kind of a waste of time. Now, this, here's one. You may have received this in an email. The one that I recall getting is, this is the moon as seen from the North Pole in the summer, okay, where the sun is always up. No, it's not. The moon is never, ever going to look that big in the sky compared to the sun. They are about the same size in the sky, all right? Each covers about half a degree. So you're never going to see that. So that was a nice job with Photoshop. That brings up another point about the moon. It's the so-called moon illusion. That is, we've all looked at the moon, the full moon, as it rises, and it looks enormous. This great, big, orange ball right on the horizon. And you think, how could it be so big? Because once it gets up in the sky, it doesn't look anything like that big. So what's the explanation behind it? Well, I've heard people say, well, it's refraction in the atmosphere, bending of light in the atmosphere, that actually magnifies the moon. No, it's not. It's an illusion, and it's not totally explained. The explanation that makes the most sense to me is that when it's on the horizon, we have reference points in terms of angular size. That is, we know what the angular size of houses and trees and towers and that kind of thing are, because we've seen them a lot. But when it's up in the sky, we have no angular size reference points up there. You can test this for yourself. Next full moon, if it's clear, go out and measure it, okay? You don't need any elaborate equipment to do this. Take a pencil. Just hold a pencil up at arm's length. The pencil or its eraser will just about cover the full moon. Or if you forgot to bring a pencil, use your little finger. It may be a little bit bigger than the full moon, but that's okay. Look at that, and you'll notice that the full moon is just about fully covered by your finger or by the pencil. Go out a few hours later when the moon is higher in the sky. You can do this, even if your bedtime is 10 o'clock, because the moon will have risen considerably. Try it again. It's going to cover the same amount of space, all right? So you can prove that the angular size of the moon does not change. It is not magnified by the atmosphere. The best explanation, again, that makes most sense to me, there are others, but this one is the most sense. You've got angular size reference points there, and that's why it looks so much bigger. It isn't really. Lunar months. There are a couple of ways of describing the lunar month. Actually, there are more than that, and we'll get into that in the second talk. But for this part of our voyage of discovery, 2 ways of looking at it. That's the sidereal period, that is, as against the starry background. The sidereal comes from a Latin word, sidus. That's one Latin word that means star. The other more familiar Latin word meaning star is stella. Whenever I hear that term, I always think of Cat on a Hot Tin Roof and Marlon Brando's character yelling, "Stella!" But the sidereal period is the moon's period as seen with respect to the background stars. It's 27.3 days. But the synodic period, and this comes from a Greek word, synod, is a meeting place or a crossroads. And you speak, it was used a lot in church organizations, a synod of bishops, a meeting, a congregation of bishops. The synodic period is one revolution around the earth with respect to the sun. That is, from one new moon to the next is 29.5 days. Could be from one full moon to the next, but it doesn't matter. It's one phase of the moon to the corresponding phase a month later, 27.5 days. Okay, 2 days difference here. Why? This is why. Position A, the moon is directly opposite the sun. That is, the moon is full. Okay, Earth in between, seen against the background of the stars over here. 27.3 days later, here, the moon's sidereal period, it's made one revolution around the Earth, and it's still opposite that same group of stars or constellations, but it's not opposite the sun. It would have to be here, since the Earth has moved 1/12 of its orbit around the sun, and the moon is following along. So the moon has to move 2.2 more days before becoming full again at this point, and therefore the synodic period is 29.5 days. In our last talk that Bill Busler gave last month, the same sort of the same thing, the solar and the sidereal day. The sidereal day with respect to the stars, the solar with respect to the sun. And if you missed that, you go on YouTube and you get it. Okay, eclipses. They can only occur at the time that the solar eclipse can only happen when there is a new moon, that is, when the moon is between the Earth and the sun, because that's why we have an eclipse. The moon casts its shadow on the Earth. And the moon has to be precisely on the ecliptic. Now, as I think we've already mentioned, the moon's orbit is not coincident with the orbit of the Earth, the orbital plane of the Earth. It's inclined about 5 degrees. So that's why we don't have an eclipse every month. If the moon's orbit were in the same plane as the Earth's orbit, we would have 2 eclipses every month. We'd have a solar eclipse and a lunar eclipse, but we don't. And the reason is the moon's orbit is tipped just a little bit, so that it's either going to be a little below the node, as it's called, or a little above. So this is the geometry, and you see here, here's the sun, moon, and the Earth. This is the central part of the shadow, the umbra, and this is the lighter part, the penumbra, pen being a part of a Latin term that means almost. So it's umbra means shadow in Latin. A penumbra then is an almost shadow, like an insula in Latin is an island. Peninsula is almost island, like Florida or Crimea, where the principal river is the Crimea River. The solar eclipses only at the time of new moon, and here's where we've already talked about that. Here's the geometry of it. And we've already mentioned, too, that the sun and the moon appear to be the same size in the sky, half a degree. This is the only planet in the solar system where this happens. There are moons around other planets, and they do move across the sun as seen from those planets, but none of the moons is the same apparent size in the sky as the sun at that point. So in this solar system, as of now, this is the only place where you can see a full solar eclipse. It won't always be the case, but that'll be way after our time. And as we mentioned, I think briefly, the sun is 400 times the diameter of the moon, but it's also 400 times as far away. So they look the same size in the sky, give or take a little bit. And we'll get to that in just a moment. But there's several types of solar eclipses. First is the total eclipse. That's what everybody looks forward to. The moon completely blocks out the sun, and what you can see around it is the corona, the Latin word for a crown. And this changes its shape, as we'll see in just a moment here, changes its shape depending on solar activity. In a partial solar eclipse, And this is the one, a lot of us have seen one of these, where the moon sort of takes a bite out of the sun. Here, the penumbra, the outer shadow cone, the partial eclipse looks like it's taking a bite out of the sun, and then there's an annular eclipse, not annual, but annular. Both come from the same word, meaning a ring, but the annular eclipse is where the moon is too far away in its orbit to block out the sun completely. It does block out most of it, and this is one you cannot look at directly unless you have eclipse glasses or some other suitable protection for your eyes. This one, at totality, you can pull the glasses off, and it's safe to look at, but not these two. I have seen an annular eclipse. I was trying to take pictures of it, photographs of it. This is 1984, and I was clicking away, and I thought I'm going to have a real great series of photographs here. And after it was over, I took the camera off the telescope, and I was going to just use up the rest of the film and photograph the site where I was observing. And I kept taking pictures and I kept thinking, there's not that much film in the camera. And to my horror, I realized what had happened. This is not going to happen with a digital camera, but it sure would with a film camera. The little leader, the tongue on that film, had not fully engaged with the take-up reel, and so the take-up reel was turning, but it wasn't pulling the film along with it, so I didn't get a single picture of that eclipse. But the eclipse is annular, not angular, annular, ring-shaped. And this is sort of what you see. The moon approaches the sun, and then it completely blocks it out in a total solar eclipse. This was November 3rd, 2013. You see the shape of the corona here is kind of round. This was at a solar maximum, but it was the weakest solar maximum in 100 years. We don't know exactly why. That is, solar maximum meaning the greatest number of sunspots in its approximate 11-year cycle. And this was in 1973, and you see it's a lot bigger. The sun was a lot more active at that time, and that's why the corona is extended to a greater extent. The diamond ring effect is what you see just before or just after totality, and that's just looking through the some gaps in lunar mountains just before or after the moon has completely covered the sun. And that's something that you have to have your eyes protected for, because even that much direct sunlight can do some damage. Here is the annular eclipse of May 20th, 2012. The one in, I think it was May of 1984, I forget the exact date now, looked very much like that. I can testify to it, but I sure can't show you a picture of it. Total solar eclipses are more frequent than you might think. We have one about every year and a half, but because you have to be right in the central part of the moon's shadow to see it, that only covers a strip of land or water, a strip of the earth, which can be several thousand miles long, but it's very narrow. And that's why most people have never seen one. You only get one at a given place on the average about every 300 years. And we will have one near Memphis. It will be a total solar eclipse in Nashville on August 21st, 2017, about 1:25 in the afternoon, Central Daylight Time. In Nashville, that eclipse will last 1 minute and 57 seconds. If you want to see the longest duration of that eclipse, you'll have to go to a place near Hopkinsville, Kentucky. And there you'll get an additional 43 seconds of eclipse if you're willing to go that far. I saw there's an ad in Sky and Telescope, or I got an email from Sky and Telescope magazine. They mount expeditions or arrange eclipse expeditions on a regular basis. And they were offering to include me in the 2017 eclipse expedition to Hopkinsville, Kentucky, and it would only cost me $5,000 to do it. I think I can do it cheaper than that. But I'm not coming from Europe or someplace either. There's also going to be a total solar eclipse in April 8th, 2024. There will be another total solar eclipse, and that will be visible in central and western Arkansas. The greatest eclipse will be in the Ouachita National Forest. You'll be able to see, if you don't want to go there, you can see, get a good bit of totality in Hot Springs, and even Little Rock is going to be right on the edge of the total eclipse in 2024. You know, I'm planning on going to see this one, and if I'm still breathing, I'm going to go see the one in 2024 as well. Now, a lunar eclipse. This is only when the moon is full, that is opposite the Earth between the sun and the moon, because it's the Earth's shadow that's eclipsing the moon. And it has to be on the ecliptic, as we talked about before, because the moon's orbit is tilted just a little bit to the Earth's orbit. When the lunar eclipse is total, you can see it from anywhere on the night side of Earth. It doesn't depend on being in this little narrow strip of land as a solar eclipse does, because you can see it just blocks out the entire moon. And there will be a total lunar eclipse. There was a partial lunar eclipse about a month ago, early April. And some of you may have seen that. If you got up really early, about 5:30 in the morning, you looked to the west and you could see the moon, and it did have a little bit of a bite out of it. That was the beginning of the eclipse. Had you been in, say, Hawaii or Alaska, you could see the whole thing from beginning to end. But there will be another lunar eclipse, a total lunar eclipse. It will be the evening of September 27th, Sunday, September 27th. And it will be total, as seen from here, and we will go out several of us, whoever wants to, will go out to Shelby Farms, out behind the operations center there at the intersection of Mullen Station and Farm Road, and we'll have telescopes and binoculars and so forth, and we'll be willing to show that to the public. It's out in what they call the Learning Arbor. It's an open shed area, but we won't be under that. And as always, we'll hope for good weather, meaning clear. And when the moon is partially in the umbra, the eclipse is partial, which is one that, well, you can see a partial eclipse from here in early April, but it was a total eclipse as seen from further west. Now, when it's in the penumbra, again, the almost shadow of the Earth, it's darkened only slightly, and you may not be able to really make that out. I've had trouble distinguishing the penumbra from just the rest of the moons in lunar eclipses. It's not that striking, but during totality, the moon may change to a coppery red. In the last couple of eclipses, the promotional flack has been the blood moon and all this. Well, the moon's never going to look like blood. Never going to be that dark. However, it can be pretty orange, pretty dark orange, and the color of the moon is going to depend on particulate matter in the atmosphere. I remember coming back from, an attempt to see a total solar eclipse. This was July 11th, 1991. We went to Hawaii and got clouded out for totality. That was the place where the eclipse would be of longest duration, more than 7 minutes, and we got totally clouded out until the total phase was gone. Then the clouds moved away. We could see a partial phase. Well, it was still a great trip. And then coming back, could look back to the west, and there was a volcano that had erupted in the Philippines called Pinatubo back then, and it had thrown several cubic miles of ash and debris into the atmosphere, and then upper winds had distributed these around the Earth. And so the moon was a really, really dark, this was not an eclipsed moon, this is just a moon. And it was really, really kind of a dark coppery tone. Eclipses occur in cycles, and we'll get into this in a good deal of detail in the next talk. There's a maximum of 7 per year. You don't always get that. I think this year we got a total of 4, solar plus lunar. And yeah, just mentioned that. Tides. People did not know what caused the tides until about 400 years ago. They guessed at it, and they usually guessed wrong. But they're caused by the gravitational pull of the sun and the moon on the earth. But the concept of gravity was completely missing. Nobody knew about gravity until Isaac Newton introduced this about, well, not 400 years ago, about 350 or so years ago. The whole idea of gravity, it just never occurred to anybody. Now, the moon is a lot closer to the earth than the sun, and therefore, the difference in the pull of the moon on the near side as opposed to the far side of the earth is greater, so it has more effect than the sun. This is not a very intuitive idea, and it took me a while to get my head around it. I'll show you here in a diagram in just a second. Okay. Then there's a tidal bulge that points toward and away from the moon, as exaggerated here. I mean, obviously it's not this great. The greatest difference in the ocean levels occurs at the time of the new or full moon because they're all lined up. So here's what the way I had to kind of reason this out. The water in the ocean feels more of the moon's gravity than the surface of the earth, the center of the earth, which feels more of the moon's gravity than the water on the other side of the earth, and that's why you get the two bulges like that, okay? They're obviously not that big, but this is what's called a spring tide. Now, it has nothing to do with the season. It's the term spring as in a source of water or wellspring, a rushing forth. And then as the earth is rotating, meanwhile, through all of this, and it's rotating faster than the moon is orbiting the earth. So it's rotating through this water, and it's going to make one revolution in one day. The moon will have moved around about here in one day, so that the tides flow in and out twice a day. You get high tide, low tide every day. And if you live on the seacoast, there are tidal tables, and you'll get in the weather forecast on TV, you'll get the tidal forecasts. We don't get that here. And the least difference is when the moon's at right angles to the sun, because it's not adding the sun's gravity to that of the moon. It does. The moon, again, exerts more of a gravitational influence on the earth than the sun does to cause tides. So the tidal bulges are not as big, and they're called neap tides. Neap tide, I tried to find the origin of that term. It's an Anglo-Saxon term. The word was neapflod, meaning neap tide. It just, nobody knows the origin beyond neap. It means neap. It means a lower tide than a spring tide. And then the very greatest tides happen when there's an eclipse during spring tides, because then you've got the moon and the sun lined up right at the coincidental point of the node of the moon's orbit and the Earth's orbit. Now, the shape of the coastline too and the latitude are important, as is the distance of the moon. So we're not going to go into that into any great extent. Now, here's something that is important over a very long time, and that is the friction of the Earth turning through the tidal bulges. This is you don't get away free when it's moving under the water. There is friction set up, and that's going to have consequences because energy is conserved. The Earth's rotation is slowing down by about a second in every 60 to 120,000 years. It varies a little bit, and because of the tidal friction, the tidal bulges don't point exactly toward and away from the moon. They're somewhat counterclockwise, so they lag a little behind the transit. Now, this has consequences for the moon as well, because that energy, some of that energy is transferred. The tidal bulges pull on the moon, transfers energy to it, puts it into a higher and somewhat slower orbit, about 3 to 5 centimeters a year. That's not inconsiderable. And that's not, microscopic. 3 to 5 centimeters. You're talking about, an inch, 2 inches a year, which you can measure easily with your fingers. But the moon is, on average, 239,000 miles away, so that's not making a great deal of difference year to year. It will, though, over a long, long time. After billions of years, the day on Earth and the moon's orbital period will become equal at about 50 of our days, so that at that point, which will be after the sun has become a red giant and then shrunk to a white dwarf, and we won't be here and neither will anything else, at that time, if anybody wanted to see the moon, they would have to go to one side of the Earth or the other. You couldn't see it from any place on Earth as you can today. And the same side of the Earth, as I say, will face the moon all the time. Okay, that's all for this segment, and we've got more coming up. So stay tuned. If you've got questions about any of this, I'll try to answer them.